Toxoplasma gondii Oocysts are typically obtained from infected cat feces and isolated using a flotation procedure resulting in a partially purified suspension. Molecular and tissue culture experiments on this parasite, however, require highly purified oocysts. To achieve this, oocysts are further purified using a sucrose flotation step, where oocysts are resuspended in sucrose overlaid with water and centrifuged to separate the oocysts away from most of the fecal matter. The oocyst layer is then transferred into a new tube, underlaid with cesium chloride and centrifuged. The resulting distinct oocyst band is then collected and washed, ready to use on experiments requiring highly purified T. gondii oocysts.
Hi, I'm Dr. Sarah Staggs, an employee of Dynamec, a contractor for the National Exposure Research Laboratory of the U.S. Environmental Protection Agency. Today we will show you a procedure for purifying Toxoplasma gondii Oocysts from the feces of laboratory-infected cats using a discontinuous cesium chloride gradient. This procedure is routinely used in our laboratory to isolate oocysts for use in molecular biology and tissue culture experiments. So let's get started.
Before beginning any work with T. gondii oocysts, important safety considerations should be taken into account. People who are immunocompromised, pregnant, or actively trying to get pregnant should not handle the pathogen due to the risk of acquiring toxoplasmosis, which can cause illness and severe birth defects. To reduce the risk of infection, set aside a designated space for this procedure and post signs to warn others before they enter the room. Remember to wear a lab coat, disposable gown, disposable gloves, and proper eye protection or a face shield when handling T. gondii oocysts. Be sure to change your gloves often and avoid touching any equipment with contaminated gloves. It's also important to work on metal autoclavable trays lined with disposable absorbent liners, and along those lines take a minute to make sure all of the racks, tubes and other equipment you plan to use are either disposable or autoclavable. If you're using non-disposable items, be sure to autoclave them after use for 2 one-hour cycles. You'll also want to connect all vacuum lines to a VacuShield filter to avoid contaminating the vacuum pump. When you're finished isolating the oocysts, you will need to apply a fresh 10% hypochlorite solution to your work surface. Allow it to dry and then rinse the area several times with water. Once the proper safety precautions have been put into place, you can proceed with your experiments. Prior to T. gondii oocyst collection, one must first prepare all of the necessary solutions for the sucrose float and cesium chloride gradient centrifugation steps. The solutions that you will need include a 2.2 molar solution of sucrose sterilized by a 20-minute cycle in the autoclave, 1 litre of TE buffer pH 7.2, a 1 normal solution of sodium hydroxide, a 2% solution of sulfuric acid, and a stock solution of cesium chloride with a specific gravity of 1.15. The 1.15 cesium chloride stock solution will be used to make solutions A, B, and C, which will be used to prepare the cesium chloride gradient. Solution A is made by mixing 30 ml of TE with 20 ml of 1.15 cesium chloride stock solution. Solution B is made by mixing 20 ml of TE with 30 ml of 1.15 cesium chloride stock solution, and then adding 12.5 microliters of phenol red solution. Finally, solution C is made by mixing 10 ml of TE with 40 ml of 1.15 cesium chloride solution. We'll begin our preparation of the sucrose float by taking a 10 ml fecal suspension of T. gondii oocysts in 2% sulfuric acid and transferring it to a 50 ml conical centrifuge tube. The source of the fecal matter comes from feces of infected cats that has already been processed through a sucrose flotation procedure previously described in a textbook written by Dr. J.P. Dubey entitled Toxoplasmosis of Animals and Humans. This additional step further reduces the amount of fecal debris in the cesium chloride purification process and helps achieve the highest purity of the T. gondii oocysts. We then neutralize the sulfuric acid by adding 3/5 volume of 1 normal sodium hydroxide solution to the fecal suspension. Mix the suspension well by vortexing. Next, add an equal volume of sucrose and mix the suspension well by vortexing. Using a 10 ml pipette, carefully overlay the sucrose fecal suspension with 10 ml of double distilled water. Once you are done, carefully place the tubes in the centrifuge and spin the sample at 1200 times G for 20 minutes at room temperature with no break. After the spin, being careful not to swirl your pipette, gently pipette from the air-water interface to collect the top water and interphase layers. It's very important to try to minimize the amount of the sucrose layer that is carried over while you're collecting the interphase layer. Transfer these layers to a new 50 ml conical centrifuge tube. Vortex the tube to mix the remaining sucrose fecal pellet solution. Repeat the previous water overlay and centrifugation steps once more. After the spin, collect the top water and interface layers and transfer them to a new tube. Use double distilled water to bring the volume of the two oocyst interphase solutions to 50 ml. Then centrifuge the tubes at 2000 times G for 10 minutes at room temperature. Finally, aspirate the supernatant from each tube. Resuspend the pellets in 5 ml of TE buffer and pool the oocyst suspensions. The oocysts are now ready for the cesium chloride gradient step. We'll start by preparing a discontinuous cesium chloride gradient in a 50 ml polycarbonate oak ridge tube. To the polycarbonate tube, add 10 ml of the suspension containing TE and oocysts. Using a 50 ml syringe with an 18 gauge blunt-ended autoclavable steel needle and a two-way stopcock, slowly add the following solutions directly to the bottom of the tube. 8 ml of solution A, 8 ml of solution B, and 8 ml of solution C. Make sure the flow rate doesn't exceed 0.5 ml per second. It's also important to note that the phenol red in solution B helps distinguish the gradient layers. Now you're ready to centrifuge the oak ridge tube at 12,000 times G for 60 minutes at 4 degrees Celsius with no break, using a fixed angle high-speed rotor. Now that the centrifugation is finished, we collect the opaque white band between solutions A and B. This band contains the oocysts. Using a 10 ml pipette, go directly to the oocyst band without disturbing the gradient and collect the oocyst. Try to minimize the amount of cesium chloride solution that you aspirate while you're collecting the oocyst, because excess cesium chloride might make it difficult to pellet the oocysts during the wash step later on. Transfer the oocysts to a new 50 ml conical centrifuge tube. Now, wash the oocysts with 30 to 40 ml of double distilled water, and then centrifuge the tube at 2000 times G at room temperature for 10 minutes with no break. Carefully aspirate the supernatant, being careful not to disturb the oocyst pellet. Repeat the wash 2 more times. Once the final washes have finished, carefully aspirate the supernatant and resuspend the pellet in 10 ml of 2% sulfuric acid. Check the oocysts under the microscope to ensure that all fecal debris has been successfully removed from the sample. The oocysts are now ready for further manipulation, or you can store them at 4 degrees Celsius until you're ready to use them. Here is a look at what unpurified oocysts look like using a differential interference contrast microscope at 400x magnification. Notice the presence of large amounts of fecal contaminants in the field, making it very difficult to identify the oocysts. Here is what the oocysts look like under 400x after the cesium chloride gradient purification protocol. Notice the absence of fecal debris.
We've just shown you how to purify Toxoplasma gondii oocysts from the feces of laboratory-infected cats using a discontinuous cesium chloride gradient. When doing this procedure, it's important to remember to follow all safety guidelines and to always be careful when underlaying the cesium chloride gradient by adding each layer very slowly and trying not to disturb or mix the gradient. So that's it. Thanks for watching and good luck with your experiments.